Recording started, good. And potentially also what we can also observe, however, is that these types of heat waves, for instance, occur in new locations. If one thinks, for instance, of the record-breaking Canadian heat wave. When we are on compound event research, something we are very interested about is, however, to understand combinations of these potential events. And in general, when we speak about compound events, we define a compound event as a combination of multiple drivers that lead to a significant amount of risk. So any type of multiple climate event that leads to significant socioeconomic impacts. And the reason we are interested in these types of events is because we tend to observe that when we have multiple climate events, so for instance, multiple extreme events, that in comparison to the single extreme events, the impact is even accelerated. So this is a figure I adopted from this paper of Zeichler et al. 2018, which shows this type of thinking. So we can have here, for instance, on the x-axis, one climate driver, which could be a heat wave. And then on the y-axis, we could have, for instance, humidity. And then this hazard could be, for instance, a human stress. And in tendency, it is that, of course, when it gets hotter, we also experience more stress. But this becomes even worse when there's also humidity in addition. When we are in agriculture, for instance, this is another example. So agricultural stress, this one could be humidity, and this one could be drought. And we see in tendency the worst impacts when we have strong droughts combined with strong heat waves. To perhaps show some numbers also about this. So this is one figure I took from one study that shows the likelihood of observing agricultural impacts during dry events, hot events, and dry and hot events. And this study was conducted for maize, and those are the 5 most important maize-producing countries. And you can see that the likelihood that we observe a yield loss is always the highest during the dry and hot events when we compare it to the single events. So this is the basic observation we often make when we are doing compound event research. And this here are so-called multivariate events, meaning we have multiple climate events occurring at the same location. However, something which can also occur is that we have some sort of spatial dependencies. So this is a figure I took from another study which focuses on the 7 key wheat producing countries of the world. And the question here was whether it can occur, for instance, if I have a heat wave in the United States, that this triggers also a heat wave in another region of the world. Basic thought behind this is, of course, if I have a heat wave or dry event in one country, this can lead to agricultural impacts. This could, for instance, affect prices on the market. And if I have multiple failures over the world, this becomes even worse. And this type of study was indeed our main motivation for CLINT, so to say, when we want to study the interconnections of drought and heat waves. Indeed, we want to understand how these types of events are connected globally. So we want to understand the global interconnections of large-scale droughts and heat waves. And what we mean by large-scale events, I just want to say this shortly, is that if we want to, for instance, define a large-scale heat wave event in Europe, what we do simply is we take a gridded data set from the European domain, which could be the ERA5 data set. Then for each of these grid points, we perform a detection using a heat wave index with which we can identify heat waves or not, so zeros and ones. And then all those time points where in this region, for instance, Europe, we observe that at least 20% of these grid points are affected by heat wave condition. We call this a large-scale event. Yeah. So we are considered here mainly in this follow-up in the study that we are conducting. If we then obtain these time points of these large-scale heat wave events, for instance, in Europe and the United States, whether we observe that these time points are falling together in tendency or not. And for that purpose, however, when we want to conduct these kind of studies, we need to be a bit cautious. The reason we need to be a bit cautious is because extreme events are also themselves changing over time. So we are looking now at multiple extreme events and we want to assess their dependencies. However, what we know, especially from heat waves, is that we have an increased frequency of those types of events. And this can lead to problems when you want to assess dependencies. So for instance, if I take a time series, which is somewhere in Europe, and another time series of temperature records in a remote region of the world, you will see that both time series will in tendency go up. But this is because we have the global warming signal. And if you put now simply a correlation of these two upgoing time series, likely you will find a significant correlation. But this is because they have the same signal behind, which is causing this correlation. So for instance, if I would perform detrending of this time series, it is not guaranteed that they are actually connected. So we need to be very cautious that we distinguish this change in frequency signal of the individual events and the dependency signal. And for that purpose, we are using a tool which was proposed here, which is the so-called inhomogeneous J function, which is able to account for that. And I just want to show this in the next couple of slides, what we are doing with this tool within CLINT. So say now, for instance, I will now give some examples. We are interested in identifying when I observe a heat wave in a certain country. Then I want to assess whether I observe perhaps a higher likelihood that I observe then a drought in a second country. Then I would collect those large-scale events, which are the time points at which these events occurred. So and then, for instance, it could look like this. So these are then the time points in the first country, the red ones, in which I would have observed a large-scale heatwave event. And these are the time points in the second country. And if I observe something like this example, I see that always after I observe this first event, there's a second event following. So which would indicate to me, okay, perhaps there's some sort of clustering of these events. We can analyze this now for a real data set. So these are just made up examples. So for a real data set, a more sophisticated data set, using this graphical tool, this so-called inhomogeneous J function. And this graph needs to be read like this. We have here on the x-axis the time distance between two events. Meaning, for instance, if I look here at the number 5, this means that 5 months after this first event has occurred, I'm curious now whether there is an increased likelihood I observe a drought in a second country. And now to assess whether there's an increased likelihood or not, we just need to look at this black line over here. So ignore for now these gray lines. So this black line here, this is a value of around about 0.9. And it means if the value is below 1, then there is indeed an increased likelihood that we observe such an event. So this is how you interpret this graph. Another scenario which could occur is that we perhaps observe something which looks like this, meaning that sometimes these poles are isolated, sometimes they fall together. So there's perhaps no clear structure behind. In this case, this would correspond towards independence, in which case this J function is approximately equal to 1 for all these time distances. And the last scenario, so this was here an increase in likelihood that we observed the second event. Here there's no change in likelihood, but there can be, of course, also a decrease in likelihood. So which is the so-called inhibition scenario, in which case the J function is above 1. And why we are now using this tool is, as I was saying before, because this tool can actually absorb this type of effect that this observation of time points throughout the timeline is now changing over time. So this is something we do not need to worry about here. This is why it's called an inhomogeneous estimator. If you want to know how, I'm happy to say something about that after the talk. But for now, let's focus here on these. Let's stay with this over here. And so this is why we use this tool. And some of you might think, okay, this tool is nice, but you need to, of course, look at graphs, which is not very good. Because in some cases, you can also have graphs which look like this. So in which case, this decision as to which dependent structure this belongs now is not that unique. So this graph here, for instance, could indicate that for a certain while, my likelihood is increasing that I observe an extreme event in a second country, but then it reverses. Now, some people might think, so you can start to think, okay, that I observe dependency for a certain while, and then independence might be something which is realistic, because we simply lose the signal when the time distance is increasing. But on the other hand, if I look at this graph, I could also be not 100% sure, perhaps, if this is just an oscillation due to statistical uncertainty, and it's just oscillating around the one line. So here in this case, depending on who looks at the graph, the decision can be non-unique. And this is, of course, not nice, so the interpretation is a bit subjective. The second thing, some of you might have also thought about it already, is now, let's say I want to look at thousands of potential time points that fall together, then I would need to look at thousands of graphs. And this is not feasible. So although this tool is perhaps nice, these are apparent problems. And what we have done now in CLINT is we solved this type of interpretation or issue with machine learning. We wanted to have an automatized tool which interprets these functions. We did this as follows. So we had the idea that simply, okay, if I would now would like to learn how a J function works, so if I want to be the perfect interpreter, something I would need to look at is simply a lot of functions. And this is something we can show a machine. So what we have done is we used so-called point process models so which exactly mimic this type of dependent structure. So this whole type of theory I'm presenting here, these J functions and so on, they come from point process theory. And we can have associated models. So for instance, a point process model, which mimics independence, which is a so-called Poisson process here in this case. And with this type of Poisson process, we can simulate a realization of time points, which mimics independence. For this realization, we can estimate an associated J function, and then we know that this estimated J function comes from independence. So we can label it with independence. The same thing we can do for clustering, where we can use, for instance, the so-called log-Gaussian-Cox process model, which simulates a clustering process. We estimate the associated J function, and we can label it with clustering. Now, this procedure can be repeated many times, let's say, for instance, 20,000 times or 50,000 times. And this gives us a sample of J functions, so which are then our input features, and each of these functions now has a dependent structure, an associated label, which is the dependent structure that originally was coming from. And what we can now do is we can train a classification model, which uses those input features, and from those input features tries to recognize the label. So this is a classification problem. And this label in this case here is the dependent structure. And like this, we have an automatized interpretation tool. We have done these experiments with a couple of machine learning models we tried out. The one we were most satisfied with is the convolutional neural network. Indeed, the recognition of these types of events was relatively good. So we had an accuracy of around about 95% on both training and testing set. And I have here also the network structure in case some of you are curious, but I can say that we tried a couple of different types of networks. We also tried RNNs or simple RNNs, and the result was always somehow the same. Now what we can now do with this type of interpreter, maybe to give one example, is now if we are interested in analyzing, for instance, whether certain large-scale droughts and heat waves are interconnected, we could focus here on these three regions. I take these now as demonstration example. I took these types of regions from the Köppen-Geiger classification that came out recently. And here I took the northeastern United States, the southeastern United States, and the central part of Europe. Now for each of these regions, I would calculate the associated large-scale heat waves and drought events. I would calculate the J functions, and I can then let them be classified by my tool. This would give me, for instance, a graph like this, in which I can see now quite quickly that, for instance, if I have a heat wave in the northeastern United States, it tends to cluster with a drought in Central Europe. Or it tends to cluster with a heat wave in the southeastern United States, and so on. And like this, we have a very quick now assessment of dependency. And once more emphasizing, which is what is nice now about these type of tools, also that we can take into account these changing frequencies of these events. Now, some of you might think that, okay, we have now trained our model only on simulated data, which comes from simulated point process. So can we actually also guarantee it works on observational data? Because on observational data, we don't know the model that which is behind. And we are currently conducting some experiments. So here we have simply plotted all those J functions of this graph in one graph, all of the J functions of this table, which were classified as clustering, into this one graph, and all of those that are classified as independence. But at least here they look a lot like their theoretical counterparts. We have also made a bigger experiment, so just in case this would be also feasible. So here this is the driver is here now on the x-axis. We took the 31 IPCC regions. Yeah, this is very big, I know. The 31 IPCC regions, and looked now if drought events in those 31 regions and heat wave events trigger droughts and heat waves in the IPCC regions of Europe. We did that on seasonal basis. You see now we assess many dependencies, and they are also seasonally dependent. And we did here the same check that we took all those clustering functions and put them into one graph. And we see, however, also in this much, much bigger example that it looks like the J functions are indeed adequately captured. The same goes for independence and for inhibition. So that we can be, at least from these experiments, can be confident, okay, it appears to generalize well also on these observational data sets. Now, until now, I have mainly talked about connections of extreme events. But as I was trying to explain in the introduction, is that compound events are actually a wider class of events. So they do not only need to be combinations of extreme events, they can also be a combination of non-extreme events that nevertheless lead to high socioeconomic impact. And in this last part of the talk, I want to emphasize now on an analysis we did on compound events. And the question that arises during this analysis is basically now, let's say, for instance, I'm now here in this region, which is now resulting in this high risk or hazard. Then these types of thresholds I would need to have here and here. Do they also only need to be extreme event thresholds, or can they perhaps be also lower thresholds? Yeah. So this is something we try to analyze in the other types of compound events within CLINT. To give here a bit of information, we have 3 other types of compound events we analyzed within CLINT. The first one is a relatively warm and late winter, followed by a dry and warm spring. Here we are interested in the impacts on agriculture. That is mainly because this warm and late winter triggers an anomalously early crop growth. And this crop growth is then damaged by the following spring. So the crop starts growing too early because the temperature in the late winter is too high too early. And this is something we see, unfortunately, because also of climate change, because we have rising temperatures, and in tendency, these types of events tend to become more often. The second type of compound event is the dry winter followed by hot summer. So here we look whether drying soils in winter can contribute to increased impacts that are associated then with summer heat waves. So here we have also the impact on agriculture. We focus here mainly on grain maize, which is the most important summer crop. Then we focus here also on the hydropower generation, so in the energy sector. Then the last type of compound event has a bit of a different type of event. Here we look mainly at flooding risk. And the idea behind this event is that we focus here mainly on the alpine region. So we have here the combination of wet and warm springs. The idea is here that the warmness is triggering a snow melt in higher altitudes, which leads then to increased runoff. And then in lower altitudes, we have the additional rain which comes down, which then results in increased flooding risk. Now for this talk, I would like to talk mainly about this first type of compound event. And some of you may have already noticed that when reading this type of compound event that we use here this very scientific term relative. So, and the reason we are using this term relative is because when we studied this study, we couldn't actually come up now with exact thresholds of how we define warm or wet. Yeah, so it is not like when we assess, for instance, impact of heat waves. For heat waves, we can use typical meteorological definitions like the 90th percentile. And we would use this threshold to perhaps obtain a subset of these temperatures. And with this subset of temperatures, we want to see if those subset causes impacts. Now here we cannot really define the subset a priori because we don't know exactly the threshold. This is problematic. So if we, for instance, just set a threshold which is too low, we might have problems in reconstructing the agricultural impact. But if the threshold is too high on the other side, we might have the problem that we oversee something in terms of the impact side. So we decided here that we do this a bit differently. We don't start by defining the event, but we start by focusing on the impact. So we start by focusing on the agricultural impact. We use crop yield data for this purpose, crop yield observations. And then we try to see now which are the climate variables that drive these impacts. So which can be done with regression or classification problems. So we want to essentially identify important input features which cause these problems. And now when we have those types of features, so when we have identified those types of patterns that are behind, we can define the events. So we start here a bit differently. To give you an idea of what we have done. So we used for this analysis agricultural data coming from the AgriForecast portal. This is observational data, and we focus primarily on winter soft wheat. We decided here to go with the target region of France because France is by far the European's biggest winter wheat producer. So you can indeed show if you take the total annual production of France and the total annual production of Europe that the correlation is around about 0.5. So it is a rather good proxy. The second thing is also with new use observational data in agriculture, in case some of you may have already have experience, the data quality is quite inhomogeneous throughout Europe. So for instance, in France, we have temperature records of around about 32 years, quite homogeneous over the country. When you go to Germany, often the time spans are only 15 years or so. So which makes it, of course, then a bit more difficult to analyze. We have used 2 types of indices. So a wet and dry indicator, which is the so-called standardized precipitation and evapotranspiration index, and a crop growth indicator, which is called a standardized active temperature zone. Now what we have essentially done is we used a method which is called a kernel retroalized generalized canonical correlation analysis and a combination of so-called pre-images. What this analysis is basically doing is that we have now input features we are interested, which are our indices that I just presented, and output variables, which are our crop yields. And what this type of analysis is doing, it is basically decomposing these output features and these input features into patterns that are as strongly linked as possible. So if you perform this analysis, the output, for instance, for the yields, which are in this case now here our response variable, would look like this, that we have 3 different types of patterns. So you interpret these patterns similar as an EOF analysis or principal component analysis, in case you are more familiar with that. But maybe to just explain it once, it means here that you see we have here these red values. These red values here correspond to positive values. Here, positive values are crop losses. Negative values are surpluses. Yeah. So this is basically a large-scale pattern that we observe now for which crop yield losses. And now if I look over time, so each of these patterns has an associated time series. In this case here, this associated time series is this blue time series. And you can see if those time series is very strongly pronounced, this means that we have a strong loss. So for instance, this 2016 event is a quite well-known one. So here we had a large crop yield failure in France. And in case we have negative values, it means we need to multiply it by -1. Then we have, in this case, surpluses. We focus for this talk now just on this first type of pattern because it explains most of the variance in this system, around 45%. And now for each of these patterns, you can get also associated patterns of your input variables that you're feeding into, which would here in this case look like this. So that we have here on the top, these are the values for the MP space, and this is for the SRTS. So we have done this analysis from January to May. I'm depicting here March just for demonstration purposes. And how you now interpret these red colors means here we have again positive values, which would here indicate wetness. And negative values, like we have them here in April, would indicate dryness. On the other side, here with the temperature, here positive values mean that positive values are favorable, high temperatures for crop growth, negative ones are less favorable ones. So it tells me basically if I now want to, so our original motivation, just to recall it, was to see a combination of a wet and warm late winter plus a spring drought. And now I can see from this type of analysis now, if I want to look for this wet and warm late winter, I would likely need to look mainly at January and February, because here I have these wet conditions and those warm conditions. On the other side, if I look for the drought, I need to look at April. Now, each of these patterns also has an associated time series. With this time series, now we can perform regression modeling and so on, and we can assess variable importances to assess now which are the most important months that lead to the socioeconomic impacts. In this case over here, this was the February warmth and the April drought. So that we have somehow downsized the problem to these 2 months that we can now use to assess now. Yeah, so we have downsized basically the problem to these 2 months, that those are the important ones now if we want to find significant crop yield losses. And the question we wanted to answer at last is now, okay, now how severe do these patterns need to be pronounced such that I actually see significant impacts? For that application, we used random forests and decision trees. So in this decision tree, so this is a summary of what we have found. It was shown that the most important variable for reconstructing significant losses is the April drought. And here in this case, this corresponding index needs to be -1.5. Just to say something short about this number. So this index here is a so-called standard Gaussian, so it's a standard Gaussian distributed index, meaning it has a mean of 0 and a standard deviation of 1. So in this case, a value of -1.5 means we need to move 1.5 standard deviations away from the mean, at least, to observe those impacts. So this is actually already quite in the lower part of the distribution, meaning that we have a relatively strong drought event. On the other side, however, when we now looked at the February temperatures, we found that this threshold that was extracted by this decision tree is only a value of 0.03. So just something which is slightly above the mean. Meaning that here, this type of event is something which is not extreme, it is actually quite common. So it is a quite normal warm winter that we observe here. Actually, this combination of this quite normal warm winter and this relatively strong drought is then the one that can cause significant crop yield losses. And this is something I wanted to highlight here within this compound type of analysis, so that compound events are in general not only combination of extreme events, they can also be combination of perhaps one moderate event that we have seen over here in February, so this moderate warmth, and the strong drought. Okay, I hope I was able to give you some insights now into our analysis. So I think the main thing I was trying to demonstrate is that when we compare perhaps compound events or multiple climate events to single extreme events, that the impacts that can arise here are often significantly amplified. We have developed within CLINT the AI-enhanced inhomogeneous J function, which we can use to perform a fast detection of dependencies while we take into account the changing frequencies of the individual extreme events. And we were asking in the second type of analysis that we were able to verify that actually we can also have significant impacts, here in this case agricultural impacts arising from not necessarily only combination of extreme events, so from a combination of a non-extreme event and an extreme event. Something we are currently evaluating, in case you are curious what we are now trying to do with that in the future, is here this is, for instance, for the second type of compound event, so this February warmth, whether this can be a valuable precursor for for using for incorporating it into early warning systems, meaning that if we perhaps include this knowledge of also looking not only at the drought, but also in this February warmth that is coming 2 months before, whether this can lead to an enhanced or a better estimation of risk. And we are trying to also check if we can use this threshold that we have constructed here to better estimate impacts. Good. With that, I'm done with my presentation. I'm very open for questions of your side. And thank you very much for your attention.
Yes, thank you very much, Niklas. Very nice talk and yeah, very interesting results. So maybe I suggest we have like a short Q&A round before we continue with Emanuele's talk. Yes, please. Anybody has questions?
Yeah, hello, Niklas.
Yeah, hi.
Yeah, thank you for such a nice presentation. And I really like it, the analysis you've presented. I just want to ask about the J function. The algorithm, is that open source, like the researcher like me, if we want to use in our research?
Sorry, I didn't hear you well. Can you repeat it?
First of all, I would like to thank you for presenting. It's really a nice presentation, and the way you presented the analysis, it's really good. And then my question is regarding the J function, that can we use it like, is it open source, the algorithm?
Sorry, now I got it. Yeah. So it is not yet open source, but within CLINT we are developing together with the DCAR-set softwares, which should be at the end publicly available. So at some stage it will be open source. It is not yet published, but we are working on it.
Okay, thank you. Thank you very much. Thank you.
Thank you, Amir. Please raise your hand if you have a question. If not, I do have some questions, Niklas. Yeah, regarding the J function approach. So I'm curious to learn a little bit more how you deal with that and how you deal with the non-stationarity part. And the second question, I felt that training an AI method to do the classification ultimately. I was kind of wondering whether that is really needed, and why not using simple kind of thresholds in your JSpace, where you say, expert decision like this is a connection and this is an independence, etc. And why, if you leave it to an AI, you're not really getting to the same results as a much more simpler threshold-based approach.
Yeah. So first question. So this non-stationarity issue. So this is dealt with that when you use point process approaches, you have a quantity which quantifies to you, so which is the likelihood at the at any time point, that likely a point occurs. This is the so-called intensity. And so it is the approximated expected number of points. And this intensity in very many applications is assumed to be constant over time. Yeah. So this is what I meant. This would be a constant frequency. And when you want to now take into account potential changing frequencies, you simply take an estimator of the intensity function, which is non-constant. So this is called inhomogeneous intensity function. Yeah. So in this case, for instance, the intensity could look. Let me give you. So for instance, in this case, I have a picture. Here. So for instance, this would be the so-called intensities. So here on the right-hand side, this would tell you, so this comes from this study. This is not now the data I was using, but here, this means that over the period of 1980 to 2010, for instance, for this blue intensity, that there is an increase in the amount of events, yeah? And basically, we are using this type of estimator, so this J-function estimator, which is using this inhomogeneous intensities, yeah? So this is just a tool that was recently developed. So this is how you incorporate the inhomogeneity concept.
That's in this Toretti et al. Paper, is that right?
Yes, exactly. This comes from this paper. And the second question, why AI? So we tried indeed whether we could also use some more simple classifiers. So for instance, a logistic regression, so just a very simple classifier, but it had like severe problems. So it actually showed to us that so the main problem was here that this distinction of this clustering and independence scenario. So you can see here also here we have the worst results because they are often when you simulate them rather difficult to here and there, let's say, rather difficult to distinguish by eye. And here the neural networks really did a better job. So like in this distinction of these two classes. So here we found that neural networks, so especially the convolutional ones, did really a better job in distinguishing the two. So this is why I would say this AI-based approach is needed. And I mean, in the end, why you want to have this AI-based approach is also that you can perform like very big analysis very fast. So I don't know, does it answer your question or?
No, that's no, I mean, it's elegant. That's where. So no, thanks. Now maybe yeah, I was quite intrigued by you mentioned the US to Europe connection as kind of a tailor-connected heat wave drought thing. That's actually something we also see in our work. So I was also interested, maybe more generally, what type of remote tailor connections you find in your with your approach.
So this is something we are at the moment summarizing. So I want to, we have done a preliminary like evaluation of looking which teleconnections could be potentially behind, but this is something which goes then really like after this analysis.
Yeah.
But at the moment, what I basically the most fresh result is like really this one we have obtained. And to me, it is already quite interesting that this dependencies is also apparently seasonally dependent. Yes,
Right.
there is a seasonal, really like in summer, I see much more dependencies than I see them in winter, for instance.
Yeah.
Yeah.
So you account for a 3-year lag, right, in your
at maximum 3.
classification.
Yes, maximum. So it can be anything between 0 and 3.
Yeah. Okay, thanks much. Any final quick question from the audience? Yes, Raed, please go ahead.
Yes, well, thank you, Dim. Thank you, Niklas, for a very nice presentation. I just had a quick question at the end. I thought it was neat how you decompose the yield signal, and then you have these 3 different EOFs, so to say, and then you pick up the key drivers of the first one, the one that explains the largest variability. And somehow you decide to focus on 2 key drivers because you say they are most relevant. But it seems that there are also other interesting patterns in the drivers. For instance, you have this wet signal in February and May. So in a sense, yeah, I understand that you pick the 2 most important, but yeah, would that justify excluding, for instance, the sweat signal that you see in February and May? Could there be also other compounding impact that would somehow include also those drivers?
Indeed, a good question. So when we built this decision tree that followed up, we indeed feed it into that a bit more variables. So I was now for this talk just emphasizing this too. We have also allowed here for this wet signal in February, because we originally said wet and warmth. And also potentially this warm signal we see here in April, because you have then a compounding dry and warmness, so which could also be of interest. In this case here, the decision tree decided to only use these two variables for the reconstruction. And I was then playing a bit with the parameters, so you can increase the complexity of the decision tree, so it depends on certain types of parameters. But it seemed to me at least that I was always choosing this type of combination. So this comes here mainly from this method why these two drivers are chosen in the end.
Right, but that would somehow miss, for instance, the other signal that you also see, right? Like you do show somehow that the wetness and other types of signals are also quite relevant. So somehow if you limit yourself to what the decision tree picks, then somehow you're missing these potential signals, not? Just so that it's clear to me how that works at the end.
I mean, I guess this is something we need to evaluate then, perhaps. So it's a good question. It's something I need to think about as well. But here it is, so till now, this choice of variables I have done here is mainly from the statistical point of view. Yeah.
Okay.
And we can, of course, could perform some sort of sensitivity analysis if we force perhaps that these other variables are also included, whether these results change much. This is something.
Well, okay. Yeah, but
It's a
thank
good
you.
idea.
Really nice presentation. Thanks.
Thank you.
Thank you, Emmanuel.
Yeah, thanks. Yeah, it was a very interesting talk, Niklas. Thanks. I was just wondering about the J function. So if I understand right, you look at these, let's call them special dependencies between heat waves and droughts, or heat waves and heat waves, or droughts and droughts. You could also look at whether hot dry events in different regions synchronize, right? So is this something you have looked at, or it's implicit? I don't think it's implicitly accounted for here, right?
So what we can check with this function is like, as you were saying, basically two pairs. This is this remote dependency, so heat wave to heat wave to drought, drought to heat wave, and so on. Something we are also checking is we can also look at the same location, and can check, for instance, if a heat wave also triggers a drought, or vice versa.
So in principle, you could also for each region define at 0, 1 time series.
Exactly.
One representing the hot dry occurrence, and then you could check whether hot dry events in different regions also synchronize, right?
Yes, exactly. So
it's something additional to this.
Yes, so
I wonder whether in principle you might get something surprising, so something that you don't expect based on results that you see here.
Perhaps, yes. So, but yeah, we can also restrict it to one region when we are having two different types of extreme events. So in general, we can apply this approach also to other types of extreme events. So the thing we need are just these time points. They need to be adequately defined. And then we can assess, do these time points cluster or not? This can be also, for instance, strong precipitation events or so, and positive phases of ENSO, or I don't know, something like that. That would also be a possibility, something we could look at.
Yes, thanks much. Let's. I suggest we continue. Maybe Niklas, if you can unshare your screen. Yeah, Emmanuel, I like to give the floor to you then.
Okay, excellent.
Yes, yeah, looks good. Thank you very much.
People there. Yeah. Okay, yeah. So, hi everyone. I'm very happy to talk here. And what I'd like to talk about today are high impact events and high impact climate. So two different things I'm going to distinguish into different parts of the talk under global warming. So when I talk about high impact event, I refer to, for example, this event we are going to look at. So a single drought that happened in this case in Europe in the summer of 2022, which was, as you can see from this time series, very extreme in terms of drought area. And for this type of event, we are going to look at the drivers and also how climate change affected indeed the drought itself. And then in the other part of the talk, I want to talk instead about high impact climates. And what I mean by climate here is in line with standard definition, basically the average of weather over, let's say, 30 years. And we are going to look at the future. So generally, we can look at maps of temperature changes or precipitation changes as shown here by these IPCC plots at a given global warming level or +2. So this is something that tells us about how the climate may change in a moderate global warming level. The question is whether we might get something that is even more extreme in terms of changes in precipitation or temperature averaged at a global scale. So can we have something like a very extreme future climate? And in this second part of the talk, indeed, I want to try to identify whether there is a potential for such extreme future climates. And this is clearly important, this type of questions. It's in line with many of the questions we ask in the community, because understanding how these extreme events happen and whether there is the potential for some future climate that are extreme can support the development of adaptation strategies for preparing to future risk. So I'd like to start with this part on the drought itself, the droughts of 2022. We have already heard about this, most of us probably. It was an event that affected many countries. This is an image for showing the Po River in the north of Italy, which was very dry. An image from the satellite in the middle showing dry condition over England and France, and then the Rialb Reservoir in Spain, which was very dry. So there were a lot of impacts across many countries. This also led overall to wildfires, reduced crop production, and limited water supply for the population. And in line with these impacts across multiple countries, if we look at the soil moisture anomaly that we could derive through the MHM hydrological model forced with TIOPS weather data, we can see that the event was very widespread. So it affected large parts of Europe. There are also some magenta point here. These are locations where 2022 was the driest simulated summer among those simulated in the last 60 years. The extremeness of the events can also be seen by looking at the time series of the amount of water in the first 2 meters of soil. We can see that 2022 was the most extreme simulated according to this MHM model, at least. And I haven't mentioned that, but yeah, the model MHM has been evaluated against satellite data of total water storage anomaly and observed river discharge. The event was extreme also when we look at indeed satellite observation of total water storage anomaly. Actually, the summer of 2022 over this region here of Europe was actually the driest since the beginning of the observation in 2022. According to our simulation of soil moisture, we also see that the event was very extreme in terms of spatial extent. And this widespread event is something we can refer to as a spatially compounding events, therefore, when many locations at the same time experience extreme conditions, and this can lead to large aggregated impacts and also potentially actually challenge response action to extreme events such as wildfires happening at the same time in many countries. So this is overall a very extreme event, and we want to ask a couple of questions here. So the first is what caused this event in terms of weather? So was it a lack of rainfall, or it was very hot, or a combination of the two? And also, how did human-induced climate change affect the event itself? So to start answering to the first question, it's kind of natural to look at the anomalies in weather. So we can see here the anomaly of precipitation in summer. So it was very dry, as shown by the red colors. It was also dry in spring over almost all of Europe, and the situation was more, let's say, heterogeneous in winter. In terms of temperature, it was very hot actually in summer of 2022. It was one of the hottest summer over Europe, and these are instead the anomalies of temperature over the previous seasons. Now, this anomaly tell us something about what would have been some drivers of the drought itself, but not we cannot really link easily this to the drought itself. So we do need to run a hydrological simulation to really quantify what's the effect of these weather anomalies into the drought, so into the soil moisture itself. And this is what we do here. We run some factorial simulation. Let's say we are interested in quantifying the contribution of precipitation anomaly to the soil moisture itself. We can run first the soil moisture simulation, so SM, based on precipitation and temperature as observed, and then a soil moisture simulation where temperature is also observed, but precipitation is rescaled in a way that there is no anomaly itself. So basically, we multiply the time series of precipitation by a scaling factor, which allows keeping the temporal dynamic of the precipitation time series as in observation, but the accumulated rainfall over the period of interest is in line with the climatology. So by doing that, we can quantify, as shown here, the effect of precipitation anomaly in summer to the soil moisture in summer. So it was dry, and therefore this led to a little soil moisture, let's say, and this is instead the effect of temperature anomaly in summer to the soil moisture in summer. This accounts also for not only for anomaly in average temperature, but also anomaly in the daily range of temperature, which is a sort of indicator of radiation that is used in the evapotranspiration scheme that is used in the hydrological model. This is the impact of rainfall anomaly in spring to the soil moisture in summer. So it was dry, and therefore it got there was lack of rainfall, and therefore the soil dried out in many areas. There is the exception of southeastern Spain, where actually there was quite a large amount of rainfall. And this is what actually indeed prevented, in the end, the drought from occurring in summer in this region, because this rainfall recharged the soil, and then this prevented the drought. And this highlights how lagged effect of weather can indeed impact soil moisture droughts, which is something in line with our understanding of how drought works. This is the effect of temperature anomaly in spring to soil moisture in summer, and then finally here, the effect of precipitation and temperature anomalies in winter to soil moisture in summer. So what we learn overall from this slide is that it was really a combination of hot, dry conditions that contributed to the drought. But at the same time, if you compare first and second row, what you learn is that it was really the precipitation deficit, the key driver for the drought itself. So without the precipitation deficit, the drought would have basically not occur, which is in line again with our understanding of how drought happen. Still, we know that there is a climate change ongoing, which is enhancing temperature, and this might enhance evapotranspiration. And therefore, we wanted to check what was the contribution of human-induced climate change on the event itself. These anomalies we see here are driven both by internal climate variability and climate change. So what about the distilling, the climate change effect? Well, we tried to do that we did that actually in this part of the work, where we compare soil moisture simulated based on factual temperature and precipitation, and then soil moisture based on counterfactual temperature and precipitation, which means time series of this variable where we remove the climate change effect. Now, the way we proceeded to produce this counterfactual, so there are many ways to do that. What we did here is to remove the CMIP6 based change of seasonal mean temperature and precipitation from the observed daily time series of these variables. And we did that by deriving trends from 23 different climate models and running, therefore, this simulation, this counterfactual of soil moisture 23 times. And then we look here at the multimodal mean. This is what we find. This is the effect of climate change, human-induced climate change on the drought itself, which led to drying the soil virtually everywhere in Europe. There are some magenta spots, dots that you see here and there. There are actually quite many. These are locations where, without accounting for human-induced climate change, we would have not been able to simulate the driest summer of the last 60 years. which means that human-induced climate change was key for the record-breaking soil moisture relative to the last 60 years of data, of course, according to our simulations. We can do something more. We can try to here instead disentangle what was the contribution of warming and precipitation trends to the drought itself. So this is what we find as contribution of temperature trends to the soil moisture. So it was warmer because of climate change, and this dried out the soil everywhere in Europe because of enhanced evaporation. That's the interpretation of this plot. And this is instead the contribution of precipitation trends, which led to wettening and drying out the soil over Northern and Southern Europe respectively, which is in line with changes that climate models show in precipitation across seasons on average. So it's not just the effect of changes in precipitation over summer, but it's really an accumulated effect over multiple seasons. Here we can take now a continental scale approach, let's say a continental perspective on the drought itself, and we can look at how much water was missing in terms of soil moisture in Europe in the summer of 2022. According to the model, we find a lack of 250 cubic kilometer of water. And based on these plots analysis we have seen earlier, we can now look at what was the contribution of climate change at this continental scale. And comparing these two, we can say that human-induced climate change caused about 31% of the total European water deficit. This was mainly due to warming, actually, because if you look at the contribution of temperature and precipitation trends, we see that the effect of precipitation trends at the continental scale, it's very little, it's very small, because of the fact that heterogeneous changes in precipitation cancel out at this scale. We then asked a further question, which is related to the fact that we know that climate change has been there not only during the hydrological year of 2022, but also well before that. So we raise this hypothesis according to which we may expect that this warming that has been there before 2022 might have started to dry out the soil before the drought, and therefore ultimately contributing to the drought in the summer of 2022. So we did some analysis to disentangle the effect of warming before and during the 2022, and this is what we found. This is the contribution of climate change that was mediated by precipitation and temperature trends before the hydrological year of 2022, a lagged effect. And this is the contribution mediated by warming and precipitation trends during 2022. So what we learned by comparing these two with this total contribution is that about 40% of the climate change contribution was mediated indeed by the warming before the hydrological year of 2022, which highlights the importance of considering the lagged effect of climate change to accurately represent a drought. You see here this 15% maybe. So this is a number which relates to the results for this lagged effect that we found by using a land surface model. So we did basically all of this analysis with an hydrological model, MHM, so all the results I've shown you so far. And then we checked again with this land surface model. All results are basically the same. The main difference is that this lagged effect with the land surface model drops to 15%. It's still large, but I wanted to highlight this difference. And also it's worth mentioning that the hydrological model actually performs better in the representation of the drought and of the climatology for soil moisture. So we have some more confidence in this model. Still, there are these uncertainty in the lagged effects that are relevant to communicate because we need to better understand where they come from. I also would like to mention, although I'm not showing an image, that we looked at a change in the spatial extent of the drought that was caused by human-induced climate change. So climate change actually intensified this spatial extent. For example, it doubled the area with record low soil moisture relative to data since 1960. So concluding on this first part, we can say that while precipitation deficit were the key driver for the soil moisture drought to occur, human-induced warming contributed to about 30% of the drought intensity and also its spatial extent, and this occurred both via direct and lagged effects. We also looked at results for river discharge, and we found qualitatively similar effects. And on this lagged effect, it's worth mentioning that we have an understanding of soil moisture memory, also climate change, but the way that we interact, it's something that has received limited attention so far. And yeah, I'd like to mention once again that we found these model differences in this lagged effect. And this is really something that it's worth further exploring, because we can expect reasonably that this lagged effect of climate change on droughts will increase in the future because of the increasing temperatures. And this really may affect future projection, and in part may also affect some of the uncertainty that we have in the projections. Also, what we learn from revealing the importance of this lagged effect is that if you look at drought indices that integrate water balance only over a few months, they cannot fully represent not only the dynamic of droughts, which is something we know, but also the dynamic and effects of climate change, because to account for the full climate change effect, we need to look a bit earlier than just a few months prior to the drought itself. With this, I'm moving to the second part of the talk, which relates to the potential for high impact global climate. So this is work about a method for identifying some potentially high impact global climates. And why is that important? Well, it's important to look at low probability high impacts future climates, because if they occur, then we can have very large impacts. So for robust risk management, we need to address them, and especially when we have large uncertainty in actual outcomes. And this is the case for climate projection, as we know. So we should really shift from solely considering the so-called most likely outcome to also look at what could be some extreme outcomes. And this is a fact that now is becoming more and more evident. For example, there are activities of the WCRP which highlights the importance for looking at risk from low probability, high impact global climates with global ramification. And this is, for example, a post from Robert Lautard, who is currently the co-chair of the Working Group 1 in the IPCC, who highlights in a post on Twitter in this weekly journal is writing on LinkedIn, for example, can end of century sea level rise largely deviate from the very likely range and rise up to 2 meters? So this is the type of question that are linked to this matter of the high impact future climates. And he highlights here the relevance of looking at storyline as a tool for indeed identifying and communicating the potential for some extreme climate. And these storylines, it's something that becomes a bit more concrete here when we look at this example, where we use them to look at regional uncertainty in future projection of compound hot, dry summers. This is in a world that is 2 degrees warmer than pre-industrial condition. And we were showing here that there is a large uncertainty in the Amazon in terms of what will be the future frequency of these hot, dry summers. This may go from 42% on average to 20%, depending on whether the climate will be very dry or more wet. This is an uncertainty, basically, that is represented here, which comes in this case mainly from model differences rather than internal climate variability. This is therefore an uncertainty that in principle could be reduced, but the point is that until we don't reduce it, we don't address it, we should really communicate it, because we don't really know where we are going. And the question I want to ask now in the following is whether this uncertainty that we see here as an example at regional scale are also large and relevant to communicate when we consider global scale climate. So when we consider climate averaged at a global scale. And it is actually in this sense, to address this kind of question, we need some methods, right? To identify this potentially high impact climates and look at this uncertainty. And what I'm showing here is that there are some in the literature, but we really need some new approaches. This is an example for a couple of the methods that are used by the IPCC to show at this, to look at these worst case global future climates. And here, for example, what is analyzed is the change in the annual maximum of daily precipitation. And what is done to communicate the potential for an high impact climate is to look at a multimodal mean change of this precipitation at an extreme global warming level of +4 degrees relative to pre-industrial. This is an extreme climate when compared to the same, but at a warming of only +2, a moderate case. And the issue here of only focusing on the multimodal mean at +4 degrees to communicate potential extreme climate is that this neglects the fact that there is a potential for climate outcomes that are extreme also if we focus at, if we reach +2 only. There might be this potential. So in line with that, actually the IPCC is also looking at uncertainties that we have when looking at a climate that is only 2 degrees warmer than pre-industrial condition. It is shown here a sort of worst case that we may get at +2. This is a map on the right, which shows the 95th percentile of the changes in annual maximum daily precipitation across models. So this is a worst case that is valid at each location individually. However, this overall map, as it is transparently recognized by the IPCC, does not represent a plausible global pattern of change as it is obtained without accounting for spatial dependencies. Basically, each model, each point represents the change of a different model, and therefore it's not a physically plausible spatial field. So to account for this issue, we want to develop propose here a new method for identifying potentially high impact global climates. And while presenting a couple of applications, I also want to ask the question, can we face potentially high impact climates even at a moderate global warming level? So the method we propose is very simple. It's, let's say, user-friendly. It allows for deriving sector-specific extreme climate outcomes from available CMIP6 model outputs. We can imagine starting with projected climate change by model simulation at a global warming level, in this case of +2 degrees above pre-industrial condition. So we have model 1, 2, and n. And what we want to do is to rank these model simulations based on a sector-specific impact indicator. This is a function f, basically, that indicates impacts to a given sector of interest. For example, if we are interested in the global food security, which relates to crop production across the breadbasket regions, we may define this impact indicator f as the change in droughts frequency across breadbasket regions. So this is a function that has to be defined keeping an impact in mind, a sector in mind, and can also account for compound events. The example I've just given indeed accounts for these droughts across different regions, but can be basically defined in the way impact modelers wish. And this is something that can be done in collaboration with climate scientists. Once these model sets are ranked, we can identify the worst models, some potentially worst case climates and best case climates. As an application here, I'm showing first the case of precipitation extreme leading to floods in highly populated areas. So as a start, we can see here the multimodal mean change of precipitation extreme in a world that is 2 degrees warmer than pre-industrial condition. So this is a sort of state of the art, let's say. What we want to do is to rank now model simulations so as to define which are worst and best case models. And we do that by averaging these precipitation changes. So this Rx 5-day means the annual maximum of the 5-day central precipitation. And we average this across populated areas because these are the areas where there is basically exposure. We are seeing these areas in the next plots where they are located. But by computing this function for each model, we can get this ranking of the simulation, which go from something I call here as a worst case to a best case, passing by from the multimodal mean. This shows that there is a large uncertainty because these worst case models, let's say, go from show an increase of 16% in the changes in precipitations averaged across highly populated areas, and best cases only an increase by 6%. We can look now at how these worst case models look when compared to the multimodal mean. So we average them and we look how they deviate from the multimodal mean. They tend to be wetter pretty much everywhere than the multimodal mean. There is the exception of this area, for example, around India. where locally this worst case scenario may be seen as something favorable, but on average at a global scale, this tends to be a potentially high impact scenario, climate outcome, let's say. And then we have this best case, which is generally drier than the multimodal mean across many areas. Now, it's interesting to ask how extreme is this worst case at +2 degrees of global warming? And we do that by comparing these worst cases with a multimodal mean of the same function f we're looking at here at different global warming levels. And what we learn here is that these worst cases are as extreme or even more extreme than the multimodal mean at +3. But this multimodal mean at +3, it's something that is often communicated as a worst case climate outcome. Therefore, this means that even if we stop at a moderate global warming level of +2, we basically cannot rule out potentially high impact global climates. It's worth highlighting here, we have not run impact models. So this is why I refer to these worst cases as potentially high impacts. As a second application, there is the case of the global food security sector and how, let's say, related to crop failure. This is the case I mentioned earlier on. As an example, we have here the multimodal mean of the change in drought frequency at in a world that is 2 degrees warmer than pre-industrial conditions. So again, a sort of state of the art. And what we do during the simulation this time is to look at changes in drought frequency averaged across key breadbasket regions worldwide. So regions where crop is produced and where therefore we expect that if there is a lot of dryness, this can lead to large impacts. These regions are being shown very soon, but let's start by looking at the distribution of this model going from the worst to the best case. There is actually a very large uncertainty here. I'm not showing here the following, but I'm just saying that this is an uncertainty that is largely due to model differences rather than internal climate variability. And what we see here is that the worst case is particularly extreme. It shows an increase of 50% in the frequency of droughts averaged across breadbaskets. An increase by 50% means that we basically go from 20% in terms of drought frequency over this area to 70%. So a very large increase in the future relative to a pre-industrial climate. As earlier on, we can see worst cases and how they deviate from the multimodal mean and best cases. So this is the average of these worst cases. It should be kept in mind that one can also look at this worst case individually rather than averaging them, so as to ensure even better physical consistency, as by averaging out multiple models, this consistency can be lost. And this is the case, for example, if one wants to run impact simulation, one should pick up the single models individually. Now, as before, we can look at how these extreme are these worst cases. And we can do the same as before. We can look at how extreme they are compared to the multimodal mean of the same function f at different global warming level. And what's striking here is that these worst case models at +2 are way more extreme than the multimodal mean, even at +4. And once again, this +4 is a worst case climate usually. I mean, it's communicated as such. So this means that even if we stop at +2, we cannot rule out potentially high impact global climates in terms of droughts across breadbasket region, and this can have therefore a repercussion to global food security. So as a summary on this second part, extreme global climate outcomes are often communicated or perceived as something that is related to extreme global warming levels. What we show here is that for some sectors, at least, potentially impact climate outcomes may also occur at a moderate global warming level. So these are these moderate global warming levels that sometimes are perceived as more safe. Well, there are some uncertainties, so we cannot be sure they are so safe. There are some research efforts that are needed here to assess the plausibility of these extreme outcomes we have identified. This is definitely very important, but until we don't disclose whether they are when disclose that they are implausible, well, until we understand whether they are plausible or not, we cannot just ignore them. There are also some boundaries to the extremeness, and this is a kind of good news in a way, in the sense that if we looked at different sectors, 4 in total, and what we found out is that very unlikely that many sectors at the same time are shown to be under worst cases. So only some sectors are likely to end up may end up in a worst case in a possible future, which makes sense because there are correlation and anti-correlation between the different variables that affect multiple sectors. Another relevant message here is that if we look at state-of-the-art impact simulation from EasyMIP, they actually neglect extreme climate outcomes at fixed warming levels. This is shown here by this case, just as an example for the drought sector we've just seen so far. This is the full spread of the model simulations in terms of changes in drought across breadbasket regions, ranging from worst cases to best cases. When we look at the models that are used by EasyMIP, they only cover the, let's call it most likely range. So they do not account for these extreme climate outcomes and their consequences. The idea is that this approach, on top of informing on what we have already seen so far, could also support the assessment of the consequences of extreme climate outcomes by basically running impact models that are expensive very often only for a limited set of climate that are retained as potentially an impact as those we have identified so far. And this may allow basically in a non-expensive way to explore potentially high impact climates and their consequences. So as a summary for the first part of the talk, we've seen that for the drought of 2022, this is an event that was driven by the precipitation deficit, but at the same time, human-induced climate change contributed to a large part of its intensity spatial extent. This occurred both via direct and lagged effect. And on this lagged effect, I believe there is a need for more research to better understand this interaction between soil moisture memory and climate change, and also in line of these uncertainties we have found in the different models we've used, hydrological and surface. And in terms of potentially impact global climate, we have seen that moderate global warming does not rule out extreme or, let's say, potentially impact global climate for specific sectors. And with that, I would like to thank you for your attention.
Thank you very much, Emanuele. Very nice talk. Questions to the audience, please raise your hand. Who has a question for Emanuele? I see a lot of clapping. No raised hands yet. Maybe I go first then. Maybe if you, on the second part of your talk, which is very intriguing and also quite alarming in a way, especially the droughts. I was quite triggered by the droughts to breadbasket analysis. I mean, in your approach, of course, you're searching for outlier models, right?
Yeah.
So the question is, I guess, typically sometimes we deal with outlier models as less reliable. And maybe that's also a reason why EasyMIP excluded them. I don't know, but so how did you look into that? Like how reliable these models still are for this specific application, these regions and the extreme event drought? Did you look into that?
Yeah, this is obviously a very important question. It's the one that I think needs to be addressed as a follow-up step. In terms of just going back quickly to EasyMIP, my understanding is that these models were selected based on climate sensitivity. So they represent a range of possible warming outcomes. Of course, now that we are moving more and more towards projection at fixed global warming level, it's somehow expected that given that the climate sensitivity it's filtered out by fixing at global warming level, this EasyMIP model cannot well represent the full range. And going back to what you said, it's again the next step to look at whether these models are let's say plausible or not. simply being outliers, I would argue, is not a good reason for saying they are right, not trustable. And this is the indeed key point of this analysis, highlighting that there are these outliers, and now we should really check out whether they are plausible or not. But I think it's important to communicate that they are there, because ignoring them could be, could lead to bad surprises. I mean, we are seeing in some cases, right, for climate model simulations, that observations are really at the tail of what models show. We discussed it, I think, here in Leipzig, this change in the jet stream, right, over Europe. We see there that the models are really at the observations are at the tail of the model response. And we have also seen recently a paper coming out on heat waves in PNAS from Kai Korumber showing something that is inconsistent with that. So it's something to definitely explore. Yeah. But it's the key question. It's the key question.
Yeah. Thanks for your answer. And I fully agree that we should not ignore models simply because they're outliers. we should look into them. Any questions? Elena, go ahead.
Yes, thank you very much. And thank you very much, Emanuela. That was really a great presentation. I really enjoyed it. So I have a question, but I'm going to the first part of your talk, because you were discussing about the lagged impact actually to the case of 2022 event, because it's not just drought, it's much more than that. Have you considered in this, I mean, how long, first of all, it was that lag, if I'm not mistaken, are you going to the 1st of November, 2021, right?
It is correct, yes.
So I was wondering whether actually the very extreme years, 2018, 19, and 20, which were actually important and caused a severe impact in larger parts of Europe, whether that would be also a contributing factor to what happened actually in 2022. We have, we have a short, we have a paper coming out from ClimExtreme, where we are looking on what is happening with the soil moisture at deeper layers. So we saw that even if there was a kind of an increase or trying, a bit more precipitation than, not as dry years, still it took quite some time, or it hasn't even yet recovered after the consecutive extreme dry years. So what do you think? Would that go?
I think it's very interesting as a topic. I didn't quantify how long this lagged effect of climate change goes into the past. I can only say, it's definitely, which kind of makes sense, right? It's not more than, let's say, not more than 15 years, based on the model I looked up, which it's not very informing probably. But the effect of previous drought definitely might be there in 2018, especially in areas where there was no recovery. And this recovery, I agree with you, depends very much on the depth that you look at, right? We expect the surface to recover more quickly because it has a high frequency variability related to the weather itself, but the deeper soil suffer from that, definitely. Actually, we are going to start a project next year, a so-called CISO project here at UFZ, a PhD course, and I'm planning as a first, this might change always, but the idea was actually to do what you just said, with looking for this sequence of droughts in Europe, and how this somehow affected the follow-up years. So this might also be eventually some areas for collaboration if you are interested. But it's really interesting, I think.
Right. Thank you so much. And thank you again. It was really great.
Yeah, thanks actually for that. Yeah.
Thanks, Elena. Paolo?
Hi, do you hear me?
Yeah, we see the uncertainty partitioning in the back.
Right, yes. Thanks, Emanuela. Great talk, very clear. And it was really fascinating. So you see, I pulled up the Ed Hawkins classic plots, splitting the model uncertainty to the internal variability to the scenario uncertainty share of explaining precipitation and temperature there. So I was really aghast to see the implications of these plots in a concrete impact case, such as you show here. So yeah, it doesn't look concerning when you see that the model spread is used for precipitation in blue. So the blue area indicates the model spread in my plots behind me. But that, this is, for example, for the droughts in the bread baskets, it's got, I'm wondering, how should we start to depict the implications of each of these plots, as you say? Or rather, let me ask you, are we looking here more at the temperature effect of model uncertainty, or at the precipitation model uncertainty in the results that you've shown?
Okay. I believe this is uncertainty that is largely not driven by temperature. Well, to a first order, because of the fact that we are fixing the global warming level, right? So in a way, this uncertainty from the warming itself, which can enhance, for example, precipitation extreme, it's filtered out. Although in part might still be there, because, if there is a local model, a different ocean land contrast, then if you look at precipitation over continental areas, this might have an effect in line with what you suggest. And it's a question. I can. Let's see if I can do this poor stuff to kind of answer to your question. Okay, here and here. So if you look here at this, you see my pointer, right?
Yeah.
Okay, good to know at the end of the talk. So it's this is the distribution of the models, and in this case we picked up one ensemble member per model. Okay, so you don't really know whether this uncertainty is coming from model differences or internal climate variability. And then to try to provide some information on the source of this uncertainty, we picked up here just one single model, which is a SMILE, so which has 50 realization, and we checked what's its spread. This is instead another model. And what you can see here is that internal climate variability explain definitely some parts of this uncertainty that we have here, because this is not very small, although model difference are still quite relevant, because you see this uncertainty from all models is way larger than the one from internal climate variability. And here instead, it's the same for droughts. What you see here is that the overall uncertainty we get is way larger than the uncertainty from internal climate variability. And therefore, this means that most of this uncertainty we see here comes from real model differences. So at least some of these models are wrong. We just don't know which are those that are wrong. And this is what we need to understand. But at least it's a reducible uncertainty. So we can try to do something. We should do something, to try to.
Sorry, the realizations you picked are random. So could it be that if you picked even to show here, it could be even a wider spread if you picked the most extreme?
On this orange, this larger bar, I don't know what color is it.
That covers everything.
Yes, you're right. It's one member per model. So it's possible that this model here, if we pick up other members, might be higher or lower. Well, definitely will be higher or lower.
Thank you.
And exactly.
Thanks, Paolo. There's actually a question in the chat from Sifang Feng. Sifang, would you like to ask your question directly to Emanuele? Or maybe I'll read it out loud. Thanks for the very nice talk. I have a question about storyline. When you focus on worst and best case, how can you confirm if they are plausible? I mean, the worst case indeed is pretty extreme, as you show, but they might not be plausible. If so, this might not be what we really care about.
Yeah, it's related very much to the question you asked.
True.
So it's we need to address the idea here is to highlight that there are some outliers. Let's call outliers. I don't know what we should call them, because in some cases they are not really, they are more or less outliers. So there is a spread in this distribution, and then we need to understand what's the most likely thing to happen in the future. Emergent constraint could be a way ahead, although it's not always simple to find them or to trust them, to inform on what is more likely to happen in the future.
Yeah, I mean, did you look in like for these worst case drought models? Did you look maybe into historic trends of the models and if they are
I think this is
reasonable?
Absolutely. Yeah, this is also something I was thinking about. I suspect that here one limitation might be the fact that the drought observations are soil moisture observation, right, are limited, short, and they cover generally the surface only. So when we look at data that cover the full soil, in reality they are still a reconstruction based on models. And then the question is, can we trust that? Total water storage anomalies are something that would be more reliable from GRACE, I believe, but these start only in 22. So there are only 20 years of data. But the more we go ahead with observation, the more these things start to be feasible. So it's worth looking at that.
Yeah. Well, thanks. We have to wrap up here. I would like to thank both of you, Niklas and Emanuele. Really nice talk, and thanks everybody for participating. I think we had some